Next, we're going to be going over to synthesis. So before starting, we need to prepare our workspace, and we did this in the simple example. And really, if you haven't watched the simple example and all of the videos beforehand, I really suggest that you go over them, how I build my project workspace, because this is quite important. But just as a reminder, we have the libraries folder, this one over here, and we set up a technology and standard cells in the previous example. So we saw how we did this for the synthesis on the simple block. And now what we have to do is provide things that we didn't have before, which are the definitions for our IO library. So we have a file there called libraries dot whatever our IO library is dot tickle, and for the SRAMs that we compiled, which is libraries dot whatever our SRAM names are, and then tickle, and we have to go and really set up the different definitions for that. So I'm not going into the exact definitions that we use for a specific library, but that's where we would add these definitions and then read them in. And this enables us to bring, different IO libraries, different SRAM libraries, or any type of different custom hard macro type of thing, or even soft macro that we want to bring into our design. We provide it a different file inside the libraries and optionally read it in. Then we have the inputs folder, and in the inputs folder we have our top level name, defines, so that's our defines file, and that's an important file that's going to set up all kinds of things. It's going to set up a lot of these variables over here. So it's the target period, the ports, etc. Provide instance names of the hard macros. So so we want to know what these SRAMs are that we're going to be using in our design. We're going to set up the SDC file. So there's the whatever our top level name is .sdc, and if we need to, we have to make changes to the MMMC. We probably don't need to make that many changes because they're mostly set up for our specific library that we're using. But now we can go ahead and start synthesis. So we're now ready to move on to synthesis, and just before we start, I will run Genus over here to get it running by the time we're ready to start. And let's look and see what we have. So again, in our source code folder, we have the RTL of the SoC and of the RISC-V core, and we also have this file RISC-V source list. And if we go over the RISC-V source list, there are all these system verilog files, as we can see here. At some point, we have the wrappers of the memories, and what we're going to have actually is we're doing synthesis, so we have to have lib files of the actual memory instantiation itself, which we created from compilation. So let's see where we did that. So under this memgen folder, I have a SP16384 by 32 subfolder because that's the only size memory I'm going to be using, and I have two options of it. I have one that's a MUX 16 and one that's a MUX 32, and that was just to have kind of different aspect ratios of the SRAM to make it more interesting. And inside that, I can see that I have different data sheets. I have lib files for different process corners that I'm using. I have the left file, and I have a .v behavioral file for the SRAM over there. If I go back to this list, I do not have the .v of the actual SRAM itself, and that's because I am not running a simulation right now, which I would have had if I was looking inside, for example, not under here, under the test bench, I had the source list. I had to have the actual, I had to have some sort of file that's describing my SRAM. We actually kind of wrapped that away with these simple type versions of it, but I could have used the actual .v file of the SRAMs in there. But for synthesis, I need lib files. So I'm now we saw over here that I do have the lib files here for the different corners. Okay, and I need the left files for place and route, of course, and for physical synthesis. Okay, so under my RISC-V source list, I just ended the wrapper, and it's going to find the actual instantiation of the SRAMs as leaf cells. The other thing I have is a file called dummy p corner, and the reason I have that is because in my IO ring, I have corner cells that enable me to make the turn and connect all of my power rails, power rings that go around and so forth. And these are just cells that don't have any logic inside them, and therefore they don't have any type of thing that needs to be synthesized. So what we did is under our libraries file, we created this empty kind of dummy called pcorner, so it would be bound to something. We don't have to create anything in synthesis, so this is just a kind of dummy empty type of module that we provide here, just so we could pass the elaboration of the design. Again, there's nothing inside, but we do have to have this pcorner module to, in the end, we have to provide a left for it and so forth, and that we do. We do have a left for it in our IO library. Okay, so this is what we have here, and of course we're going to go and use our scripts file to load our Genus tickle script. That is what we're going to be running over here. And we have our libraries, which are all the files we need for our PDK and our standard cells. We also have the SRAMs, so we had to actually define the SRAMs in here. So let's look over here. We added, to all lefts and all WC libs and TC libs and so forth, we added the SRAM, the relevant things for the SRAMs that we're going to be using. We did this with kind of some scripting over here. And we also mentioned what the core and peripheral VDD and VSS names are. So these are just definitions that are specific to SRAMs that we had before. Another thing is IOs. But for the IOs, we also provided all the data about the IOs over here, including, for example, what the VDD core, ground core, VDD IO, and ground IO of these guys are. So really, we have we added our definitions to what we did in the previous, simple kind of design of what we need. Okay, and we have a regular, standard cell file and PDK file. In our inputs, we have the defines file, which defines the things for our design, that the clock is from clock and the clock port is pad clock, and we define the period and all of the rest of the things. We define the hard macro names, which we saw we have 2 instruction memory instances of 16K by 32, and we have 2 data memory instances of the same size. Okay, and just all of the things that we need in our defines file. And we have the other files we need: the SDC, the MMC, the floor plan defines, CCOpt, and we have another thing called IORing, which I will get to in a little bit. So now we're ready to start our synthesis, and of course our design top level is LP RISC-V top. That's the first thing. We said that was the top level module name. Our run type is synthesis. We're going to use a physical synthesis type of LEF. We're not starting with a floor plan over here. We're going to read in our procedures file, and we're going to start our design. Okay, we have our debug file. We're going to read in our defines. We're going to read in our settings. We're going to read in all of these library files. So now that we've read all of that in, we're going to suppress some messages over here, print everything to the debug file, and I guess we're ready to go. So now we can start the init design stage. And at this point, I am ready to load my MMMC file. So I will read MMMC, and this takes a couple of seconds, maybe a bit longer. On advanced nodes with a lot of corners and so forth, it may take a lot longer. Okay, we read that. We don't see any problems over here. Okay, then we're going to read our left files, and now there are going to be many more lefts than we had before, because we're also reading the lefts of the memories and of the IOs, and we get a couple of warnings about them that I didn't suppress, but these are okay things. These came from the library itself. At this point, I'm ready to read the RTL, so let's start this stage reading RTL, and I'm going to go and I'm going to read my RTL from the read HDL list. And if I look over here, it read everything, and there are no errors in reading this RTL, so that is good. So during the synthesis, many things are reported to the log file and written out as saved reports, and we should check some of them. So which ones should we really check? Well, we should check warnings. In general, there are a lot of warnings that are spit out in all the log files during the entire EDA flow, and a lot of them are just there to drive us nuts and conceal things that are really important. But during the init design stage especially, and actually the other stages, there are warnings that are spit out, and we should look at them and see if there are problems about things like the libs, lefts, the RTL, if we didn't provide something correctly, and that type of stuff. So really, we should go over these warnings and so forth. And actually, you can suppress messages if you see that something, you know what it is. It's maybe a feature of our lib lib or our lef that we're reading in that was provided by a vendor, then we can suppress the message so it doesn't bother us afterwards. But it's an important thing to have a checklist that when you're going over a project, you should really go sincerely through each and every single one of those warnings and make sure you know what they are and understand if you can not pay attention to them or there's something that you need to fix. So a super important thing during synthesis is unresolved instances. So when we elaborate, what we're going to do is we're going to basically go and look for everything that's written in our different RTL files that we have a way to resolve it. And that means that either there is another Verilog module that answers that, or we have a leaf cell. So it could be a definition of the standard cell. It could be a primitive in Verilog that it knows how to, turn that into whatever Boolean logic it is, or it could be a hard macro such as our, an analog block or something like that, or an SRAM that we have a lib for. So when we write check design minus unresolved, it will tell us if there are any unresolved instances. And if there are unresolved instances, we cannot continue. Why does this usually happen? Because we're not going to start unless we have a file about everything, a lib file about everything, is because we often make mistakes in our paths. These things become very long with many characters, and just a little mistake like writing an I instead of an L or a 1 instead of an L or something like that is going to make a mistake in there. So really, this is an important thing to do. You cannot go on if you have unresolved instances. General design checks that you should run after elaboration include check design. When you run init design, you read in your SDC, you read in your MMMC files, and then you should run check timing intent, which is a type of a timing linter. It tells you different things about your SDC that could be wrong and so forth, so you really need to go over that. And finally, you should check your timing very carefully after synthesis with report timing, and we will be showing that later on in our in this demo, how we can look at the timing reports. Even though we're not doing something that's constrained in timing, we're not going to have to debug timing over here, but really a lot of the work of a backend engineer is to go through timing reports, understand what is wrong, and see how you can improve them and so forth. Now we can start the elaboration stage. So we're going to start stage elaborate and run the elaboration, which is going to be substantially longer than it was on our very simple design because this is a bit more complicated. It has a lot more gates than we had before and a lot more complexity. Okay, so that is done, and we have elaborated our design, and we can go and look through what actually happened when we elaborated our design and make sure nothing suspicious comes up in our log file. Okay, and so we are ready to post elaboration, check our design. So let's start with this very important check design minus unresolved. And we see that there are no unresolved references in the design, and there are no empty modules in the design. So that is all good. We have everything resolved. The next point is to check design minus all. So that we're going to actually save in a report because it's a very long file. But we can also just run it in check design minus all like that, and it will print out everything that we needed to know over here. I can go over the summary, but you need to really look at all of the warnings and all of the information that it puts out. So we don't have any unresolved references or empty modules. That's pretty important. Okay, we do have some other things, unloaded combinational pins, that's fine. We can have floating outputs, that's fine. Assigns, that's obviously we have in our RTL assigns, but we're going to want to get rid of them. And at the end of synthesis, we should not have assigns. Undriven ports and undriven pins and so forth is very bad. Multi-driven ports and pins is very bad. We have some constant pins, that's fine. Constant hierarchical pins, that's fine. Preserved leaf instances, those are probably our 4 memories that are preserved. Okay, physical left cells with no lib cells. So we should look at what those are just to make sure, but it's probably okay. So I'm just going to scroll up here, and I see that the left cells with no corresponding lib cell are all kinds of things like fillers and those types of things that do not have any transistors inside, and therefore they really don't have any behavioral model or something like that. So they only have physical info, but they don't have any lib. So these are both fillers and IO fillers and the corner cell and things like that. So this is not at all a problem. It's just something we should know about. So having got through that, I am now ready to initialize my design. So let's run the init design, and it will read in my SDC and everything, read in everything from the MMMC and see that everything's okay. And that actually ran pretty quick, and we didn't have any trouble there. I should also go over and look, and I see that there were no errors reading in my SDC. There were many successful commands in my SDC over here. So that was pretty important. Okay, and finally I can check my timing intent and see that it all worked out. When I run check timing intent, that's doing a kind of linter on the SDC. And it doesn't, the zeros are really good here. What we do have nets with multiple drivers, and that is very suspicious, and I should look at that. Timing exceptions with no effect is usually not a problem. If I have like a constraint from in to out ports, then I will probably get one of these things because it didn't find any. So let me just check this nets with multiple drivers, and I'll scroll up over here, and it says nets with multiple drivers. The following nets have multiple drivers, and at least one of the drivers is non-tri-state. So I have this LP RISC-V top pad clock enable, and I right away can kind of understand what these are. These are on my IOs, which can be either input and output depending on the output enable signal. Then I have the the pad connection is going to be possibly an input that's driven, and on the other side I have the output that is driven in a way by a custom block, which it must not know that it's a tri-state driver, and so it thinks it's multi-driven, but it actually isn't. And if I would have run using minus verbose, I would see all of this. So let's do that again. Check timing intent minus verbose, and it's going to give me all of them, I guess. And I can look over here, and I see really that all of these are all of the IOs that I have. The digital IOs appear here. So that is fine, and I can disregard it. So if I have a floor plan, I would read the floor plan at this point, and I'm ready to start my synthesis. Okay, so I'm going to create my cost groups, and I'm going to provide a report timing, which I can go and I can look at under the synthesis reports directory. I'm going to set up my clock gating settings. And one other important thing I think I did mention at the problem in the previous video was that I should not use scan flip-flops. So I have a little command here that goes over all the lib cells. If it sees that they have scan enable pins, then setDB dot avoid true, which means don't use those, don't map to the scan enables, or else it can utilize the mux on the input to the scan enable cell as part of a logic mapping, and that is not something we actually want to do because it causes all kinds of problems later on in physical design. So I'm going to run that attribute, and it's going to set don't uses on all of those. Then I can set my effort levels on my syngeneric, synmap, synop, iSpatial, and on my power effort. Okay, there are more of these setDBs that I can set over here. So now I'm going to start stage syngeneric, and I'm going to run syngeneric with physical, and minus create floor plan is going to be able to kind of make an automatic floor plan and do some physical aware generic synthesis. And this will take a while. So that took quite a long time, and now that we finished, what we can do here is to run the other mapping and the post-synthesis optimization. So I'm just going to run those, and they're going to take a while to run. And now synopt minus spatial. And this too will run for a while. It's now launching Innovus in order to do the spatial, like physical synthesis. And finally, this stage was finished. So now that we have finished our synthesis, we should go to our post-synthesis reports. And for some reason, Genus sometimes forgets the cost groups that we already defined before. So we'll run NX default cost groups again, and then we can go on to report timing. Okay, and report timing is going to run and create some timing reports. So let's see what we have here. So under synthesis, we have post syn opt, and we have no into out timing. We have interreg. We met the interreg timing, and we see that we have over 4.5 nanoseconds of slack. So that's quite a lot, even though we have this type of a path over here. Reg to out timing, we also have plenty of slack over there, and reg to reg timing, we just meet reg to reg timing with only 7 picoseconds over here, and we can see that we have quite a long path going over here. So that is our timing, and since we met our timing, I'm not going to go into right now how we go through timing reports and what we can do with them, even though this is undoubtedly a very important thing to do. Okay, so once we did that, we can go back and do our other reports. So we have all of these reports that we need to do. So we have all of them, and I'm going to run them, and it's reporting them now. And after it reports them, we can go and we can see that inside our reports we have after post-syn opt, we get all these other reports. So for example, we have report area over here, tells us what the area is for the cell count and so forth. We have clock gating, and it tells us how many clock gates were made and stuff like that. Design rule, violations, data path modules used, gates that were used, the hierarchy that we have, lots of clock gating hierarchies, and some tie cells that are inside the IO ring, and the QOR. So we have all of these reports that we should go over and look through and so forth. Okay, but assuming this is all good, we are now finished with our reporting, and now we can export our design. So we're going to export the design by writing out the design and writing out the net list, and finally writing out the SDF. And this can take some time because, again, we have to open up Innovus in order to write out our database for later on opening it up inside Voltus or inside Innovus. Okay, so that may take a while. So now it's writing the post-synthesis net list, and now the SDF, and finally it has finished, and we are basically done synthesizing our design, and we can move on to floor planning and place and route.